So it frequently happens that you need to take the derivative of a function that requires both product and chain rule in order to get its derivative. So this function is an example of that. So first off, how to recognize something like that. I'm going to use the drawing loops method here again. So I see a ln x there, and I'm going to just draw a little circle around that. And then I'm going to try and draw a circle around this sine function, and I have to make sure I get its argument as well. So there's that. And then there's an x cubed up there that I'm going to draw a circle around. All right, so if I look at that, I can see that the blue bubble and the yellow bubble are multiplications, right? They are a product rule setup. So I'm going to need to use the product rule to do this piece and this piece separately. But within the blue bubble is this pink one. This ln is contained completely inside of that sine. So when I'm doing my product rule and it comes time to take derivative of this blue piece, I'm going to need the chain rule in order to do it. So what helps to get this all straight is to just build yourself some infrastructure first so that you can see which pieces you need before you start taking the derivative. It helps you to get all the pieces in the right place. So if I go to do the derivative of this, the first thing I'm going to need to recognize is the product rule structure. Product rules, as always, were take the derivative of the first thing, and I'm using square brackets to show that I'm taking a derivative, just as to remind myself. And then you leave the second thing alone. To that, you add the first thing left alone, and then the derivative of the second thing. So that's not any different. Because this is a product rule, I need the derivative of this, leave this alone, the derivative of that. The only complication arises when I go to do the derivative of sine ln x. So that's the piece that goes in here. When I do that, there's going to be a derivative of the outer layer, and then it multiplied by the derivative of the inner layer, all contained inside of that particular term. So what I end up with is a grand product rule line, right? The derivative of the thing, leave it alone, plus leave it alone, derivative of a thing. And then buried within this derivative of the second part is two pieces, right? The inner and the outer layers of this chunk. So now that I have the structure laid out, I can just go through and I can start filling in the pieces. So the thing that's supposed to go in here is the derivative of the yellow loop. So the derivative of an x cubed is a 3x squared. In this blue bracket here is supposed to be everything contained within the blue circle, just left alone. No derivatives, no nothing. Just copy it. So that's a sine of a ln x. All right. This yellow bracket is supposed to be the yellow piece left alone, so just x cubed. These square brackets are the derivative of the second piece, and it has two components to it. This would be the derivative of the outer layer. So the derivative of a sine is a cosine with whatever argument is inside. And the second piece is the derivative of the inner function. Derivative of a ln would be 1 over x. All right, so I have some gathering to do here. So df by dx, this thing will be 3x squared sine of ln x plus an x cubed over an x right? That's this thing. Cosine of ln x. Well, an x cubed divided by an x is just an x squared. So let me write that down here. X cubed divided by x is x squared. And I have an x squared in both terms, so I'm going to factor that out as well. So all that's left in this term would be 3 sine of ln x. And all that's left in this term is the plus cosine of ln x. So there you have it. Now again, just as a reminder, the only calculus that actually happened in this line was going from the function to the derivative. Everything after that was just a factoring exercise based on what you did in grade 9, 10, and 11. So net, right, in summary, if you're trying to do a function and you can do this, draw a loop around one piece and then a loop around another piece, and those loops don't overlap, you require product rule to get that done. If in either of those pieces you have loops in loops, then you're going to need chain rule in order to build the derivatives that you're using for your product rule. So we're going to do one more example of this, where there's chain rule required on both sides. And then you should be good to try the practice problems. All right. So looking at this setup, I have an x squared plus 5x here. I can draw a little loop around that. And I have a cosine x here. You can draw a loop around that. And then that cosine x is inside of a ln. I can draw a loop around that. And then this x squared plus 5x is inside of a square root. I can draw a loop around that. So looking at this particular function, I have a function buried in a function on this side. And I have a function buried in a function on this side, and then I have those two pieces multiplying each other, not inside each other. So because I have two separate sets of loops, I'm going to need product rule. And because there are loops in loops on both sides, I'm going to need chain rule in order to finish my product rule setup. So like the last one, I'm just going to set up some infrastructure. I'm going to set up brackets so I know which pieces I need and where they're going to go. So dg by dx is going to equal, first off is my product rule. I'm going to need the derivative of the yellow piece, leaving the blue piece alone, plus leaving the yellow piece alone, and then the derivative of the blue piece. Now, inside of this yellow piece, in order to do its derivative, I'm going to have to do the derivative of the outer layer, and then I'm going to have to do the derivative of the inner layer. And for this one, I'm going to have to do the outer layer and the inner layer as well. So now all that's left to do is to dig through that thing and to come up with what the actual pieces are, and hopefully my marker is fine enough to be able to write them. The derivative of any of this thing, the outer layer, it's a radical. It's going to be 1/2 of whatever's inside x squared plus 5x to the negative 1/2. The inner layer, derivative of this, will just be 2x plus 5. Leave this one alone. So I've got the first half of my product rule finished. To do the second half, I take the yellow piece and I leave it alone. And then in order to do the derivative of the second piece, I have to do the outer layer first. A derivative of a ln is 1 over whatever's inside, like so. And then the derivative of the inner part, a cosine, would be a negative sine x. So that's a whole mess there. Let's see what we can figure out and clean up. So if I look at what's in the numerators, I have this in the numerator and this in the numerator. The 2 is in the denominator from this 1/2, and this piece is in the denominator because of the negative exponent. So this mess in front is going to be 2x plus 5 ln of cos x over 2 square root of x squared plus 5x. In this term, I have a negative times a positive times a positive. It's going to be a negative overall. This and this are both in the numerator, and this is in the denominator. So I have the square root of x squared plus 5x sine x over cos x Now I could get a common denominator here, right? I'm going to pull a little dirty trick here on you first though. Do you notice that you have a sine x over a cos x? That's a thing. That's one of your Pythagorean trigonometric identities. Sine over cos is tan. So I'm going to pull that substitution because it's going to reduce the number of functions I have wriggling around in here. So let me do that on this line. dg by dx is 2x plus 5 ln of cos x over 2 square root of x squared plus 5x minus square root of x plus 5x tan x. So that has simplified this last term. I have a fraction minus a fraction, so I need to clean that up. So I'm going to need to introduce a common denominator. So let me do that. This has a 2 that this is missing, so in it goes. It's also missing a factor of x squared plus 5x. And you'll notice I already had one up here, so I just need to add in a second one. Now I'm going to write all this as a single fraction. dg by dx is 2x plus 5, the ln of cos x, minus 2. Square root squared is undone. So I'm left with x squared plus 5x here, tan x, all over top of 2 square root of x squared plus 5x. And I'm going to wager that that's as simplified as it gets. So again, just to be clear, the only calculus that happened in this process was going from the function to its derivative. Everything else was either a trig identity, a common denominator, or gathering like terms in order to package it as a single thing. So when you see a function like this and you start drawing loops, if your loops don't intersect, you're going to require the product rule infrastructure, which is a thing plus another thing. If within one of those loops there is a subloop, you're going to need chain rule when you do the derivative of your in your product rule part. Same thing happened here. So keep an eye on that. When you get to the practice problems, they either have chain rule chain rule is either necessary in the front part of the product rule, the back part of the product rule, or in both parts of the product rule. So you'll have to keep an eye out to try and see which one is which.